This presentation will give you a step-by-step method for using ChemCAD to design distillation columns and also determine how much it would cost. Before we begin, we're going to select a shortcut column to give us a preliminary design numbers to use. And this is found under the palette under shortcut, and this is what we'll be adding to our spreadsheet with the ChemCAD. Now we're ready to put in the inputs to our distillation column, and first we want to make sure that our units are correct, and you can do this by looking under the format and engineering units so that you can define the feed stream, which is stream number 1 in this diagram, to make sure that they are consistent with what you have. In this case, my feed to the distillation column has no preheater, and so it's coming in at 25 degrees Celsius. Its pressure is 1.2 atmospheres. By selecting our component unit in mole fractions, we can designate that we have ethanol coming in at 0.075 mole fraction and water at 0.925, and the total feed flow rate to the tower is 100 kilomoles per hour. The next step is to give information for the distillation column design. By double-clicking on the shortcut column, we come up with this menu. What we want to do is select the mode that we're going to operate. In this case, it's a design with a Fenske feed tray location. We input the column temperature at 1.2 atmospheres. And we also need to give it some idea of what reflux ratio we wish to use. And so a good place to start is the reflux ratio divided by the minimum reflux ratio. And in this case, if we go 1.2, we're always certain that we will have more than the minimum reflux ratio for this column. In the next area, we have to tell the column what the light key and heavy key components are. The light key in this case is the one that is most easily evaporated, which in our case is ethanol. And the heavy key component is the one that's least evaporated, in this case water. Then we have two variables, the light key split and the heavy key split. The split is defined as what fraction of that feed component ends in the distillate. In order to do this, we actually have to make a calculation using our material balance equation. And we can do this by finding out what our distillate flow is, D, by doing a material balance, one a total balance and one on a component, in this case ethanol. And we can find that our distillate flow is a function of our feed flow times the difference between the feed component mole fraction and the bottoms component mole fraction divided by the distillate component mole fraction minus the bottom component mole fraction. Using this definition, the light key split is the amount of ethanol exiting the column, which would be our distillate composition times the distillate flow, divided by what's fed. For a binary system such as this, the heavy key split can be determined by the mole fraction of water in the distillate, which is 1 minus the mole fraction of ethanol times the distillate flow D, divided by the mole fraction of water in the feed, which is 1 minus the mole fraction of ethanol in the feed, times the feed flow rate, F. We can now run our column, and then double-clicking on the shortcut column, we can get the information about the column design. In this case, it tells us that the number of stages is 11.5. We also have the condenser duty and reboiler duty. Note that the condenser duty is negative because heat is removed, which is 1.27 megajoules per hour, and the reboiler duty is positive at 1.85 megajoules per hour. We also are given where the feed stage is located. In this case, it would be at stage 9 since we have an integer feed stage. And our minimum reflux ratio is calculated to be 3.7, and the reflux ratio using our R over R min of 1.2 specifies that our reflux ratio is 4.41. So in total, our column design would have 12 stages where we would feed in at stage 9. Now in ChemCAD, it counts the condenser and the reboiler as stages. So technically, we have a column with 10 trays and a condenser and a reboiler, and this would give us the basis for designing our column. But the shortcut column is not the true rigorous design element of ChemCAD. What we really want to do is use the tower model. The shortcut column is just used to give us a basis for the original design of this tower. So we would set up a tower column whose icon looks exactly like a shortcut column, so you need to be careful. And then we would have the same feed going into the column. By double clicking on the model, we can then enter the variables into the ChemCAD menu. In this case, we'll have 12 total stages. That includes the reboiler and condenser, and our feed stage would be stage number 9. Now we go to our specifications tab, and this is where we tell the ChemCAD program how we want our column to operate. In our particular case, we're going to specify the mole fraction of ethanol coming out in the distillate for the condenser mode. And we can do this by selecting the drop-down menu to find distillate component mole fraction. We would then specify that it's 0.85 and the component is ethanol. Likewise, for the reboiler mode, we can specify bottom component mole fraction, specify that it's 0.025, and that component is ethanol. After running the tower model, we can double click on the column icon and click on the Conversions tab to get the information found in the ChemCAD simulation using this new tower model. We can determine the condenser and reboiler duty. In this case, we have a condenser duty of minus 2889 kilojoules per second, reboiler duty of 3048 kilowatts. It also calculated a reflux ratio of 43.3, which is significantly higher than the reflux ratio calculated using the shortcut model. The reason that this difference is because the shortcut model uses various number of assumptions in those calculations, particularly the constant molar overflow assumption, which is not necessarily true. This is why we use the tower distillation column model so that we can get a more accurate picture of how this column will actually work. In order to find the size of our column, we can use the sizing report, which is found by clicking the sizing menu at the top of the screen, selecting distillation, and the first thing we're going to look at is the diameter of the trays inside this column. The next menu is to select what type of tray we're going to use. In our particular case, we will use a valve tray, and also select under the printout section a simple printout. Our next menu appears, and we will go with the default values for the trays. In this case, the only variable that we might think of changing would be the tray spacing on the right hand side, but we will use a tray spacing of about 0.61 meters. We now get this report that gives us the diameter for this tower. In this particular case, if we look down to the diameter of the section of the table, we will find that the maximum diameter going down from the top to the bottom is 1.22 meters, and this is what we will use for our column design. Now we wish to design our heat exchangers, which we can do by the sizing menu, selecting heat exchangers, and the type of heat exchangers we will be using in this problem are shell and tube. The first element we're going to design is our condenser, so we would select condenser from the heat exchanger type drop-down menu. We also are then given a menu asking us to enter what the utility stream would be. In this case, our utility stream is cold water. So we would put in the temperature of our cold water, which is 30 degrees Celsius, and the pressure we can assume to be 5 atmospheres. The flow rate we will select will be 1 kilomole per hour. However, ChemCAD will actually calculate this for us. After selecting OK, we get our next menu, and we have to determine how this is actually going to work. When you are condensing a vapor into a liquid, it is usually done on the shell side of a heat exchanger. So our process, which is our ethanol water stream, will be on the shell. We will then, on the utility side, which is our cold water, tell ChemCAD how we want it to calculate its flow. In this particular case, we want the outlet temperature of the cooling water leaving the condenser to be 45 degrees C. The next menu is the calculated value of our utility stream. As you can see from the utility end, which would be stream 9, our total flow in kilomoles per hour of cooling water would be 9,213 kilomoles per hour. Now we're going to look at how we're going to introduce the cooling water and the vapor into this condenser. And you may not understand the reasons for it right now, but a countercurrent heat exchanger is the most effective use of area, so we will select that as well. We then get a temperature enthalpy diagram of the two streams. The shell side, which is our vapor that's being condensed, is approximately 83 degrees Celsius, and our cooling water, which is on the tube side, goes from 30 degrees to 45. Now we're ready to do our design, and our general specifications menu asks us for some input. Under the calculation mode, we would select design from the drop-down menu. On the tube side, which is our cooling water, the process type is what we call sensible flow, and that's because we have a material going in and not changing phase, like our cooling water is coming in at 30 and leaving at 45. There's no phase change. On the shell side, we have horizontal condensation because our vapor leaving the column is being condensed. Our next menu is our design options, and for the most part we are going to use the default numbers given to us by ChemCAD. Under the tube specifications window, though, we will change one item, and that is the number of tube passes. We will use a value of 2 in this particular case, and we find that a 2 tube pass is quite often the most common condenser style that we have. Now we'll just allow ChemCAD to give us the default values for the shell side. So as these menus appear, we are going to click OK for each one. Our next menu will allow us to do the calculations for the size of it, and to do that we would just select the Calculate button. And then we will get a menu telling us that in our particular case it took 309 iterations to converge on this heat exchanger design. The next menu we can tell it to allow us to view the results, and we want to look at a summary report. And then after the calculations are done, here's the data that we're most interested in. In this case, we want to know the area of the heat exchanger. In this particular case, it's 92.21. And in the lower left-hand column, we find that the area is specified in square meters. We also have a calculated value of our heat transfer coefficient, in this case 0.71 kilowatts per square meter degree K. And in our previous example, we were using a value of 0.6. And so that value is pretty close to the calculated value by ChemCAD. Now we're ready to design our reboiler. We would use our sizing menu, select the heat exchangers, and the type that we're going to use for our distillation column is the kettle reboiler. And it's going to ask us for the utility stream. In this case, we're using steam at 4 bar of pressure. So we would put in under the pressure 3.95 atmospheres, and the vapor fraction is 1. That means that the steam is at its dew point temperature. We then would put in 1 for kilomoles per second for the water stream and allow ChemCAD to determine the actual flow rate for us. Note that I did not enter the temperature directly. I put in the vapor fraction and the pressure, and ChemCAD calculates the temperature. Should you try to put in all three, you would find that ChemCAD would give you an error, and then you would have to choose 2 of those 3 to enter. Again, we're going to give it some information about how the steam and the liquid in the reboiler are introduced. Our process side is our liquid in the bottom of the column, and it is actually going to be boiled to turn into vapor, and we're going to introduce that liquid into the shell side. So under the process side, that will be shell. In the utility side, being steam, we will tell it that the outlet of the steam stream will have a vapor fraction of 0.0001, and that means that it's predominantly a liquid right at its bubble point. And the first thing we'll see is our temperature enthalpy diagram. The tube side, which is our steam, is a relatively constant temperature from 143 degrees Celsius down to about 142. And our process side in the reboiler shell, it ranges from a temperature of about 87 degrees C up to approximately 99 degrees C. Now we're ready to get into the design of the kettle reboiler. Our calculation mode we will select as design. Under the shell type, we're going to tell that it is a kettle reboiler, and so we would select that from the drop-down menu. The tube side is our steam, and inside those tubes we'll have horizontal condensation. The shell side is our liquid, and this is going to be pool boiling as the mechanism for this heat exchanger. We will then use the default values for the design options in this next menu. And again, with the tube specifications, we're going to do a 2-tube pass in this particular design. And then we'll also start accepting the default values ChemCAD gives for the shell specification. And again, under baffles, we will accept the default values. Same for the nozzles, clearance, material specification, along with the miscellaneous, the kettle reboiler specifications. And then will ask us if we want to update the shell inlet nozzle diameter. We would say yes, yes. And we come up with the next menu where we can do the calculations. So we click calculate on this. It will tell us how many iterations it took to converge on an answer. Our next menu is to tell it to allow us to view the results of this. So we would click that button. And again, we want to look at the summary results, so we would click that value as well. And now we get our report. We find that our reboiler has an effective transfer area of 41.95 square meters. And we calculate that the value for the heat transfer coefficient is 1.72 kilowatts per square meter degree Kelvin. To determine the purchase price of our distillation tower, we can do this by double-clicking on the column and looking under the Cost Estimation 1 menu. The column type is a tray column, which we would select, and we would estimate the column height to be 8 meters based on the total number of 10 trays. And then we would select cost estimation 2. In this case, we put in for the condenser, it's a fixed head exchanger with a condenser area of 92.21 square meters. And we'll use a design pressure of 5 atmospheres and the installed factor of a value of 3. For the reboiler, we would select kettle reboiler made out of carbon steel, and the area that we determined previously was 41.95 square meters. We'll use a design pressure of 5 and an installed factor of 3. We then run the column, and then by double clicking on it and coming back to the same menu, we see that the total installed cost of our distillation tower is $338,675. Of that, the installed cost of the reboiler is just under $97,000. The cost of the condenser is just under $72,000. And so these is the various elements that make up our distillation column and give us the value of what it would cost.